Okay, hello. My name is Hamish Steptoe. I'm a senior scientist at the Met Office, and in this presentation I'm going to be discussing the numerical simulations of historical tropical cyclones over Bangladesh that we undertook as part of the Oasis platform for climate and catastrophe risk assessment in Asia. So, the headlines from this work: we looked at 12 historical tropical cyclones that impacted Bangladesh, downscaling the ECMWF Era 5 data using a 9-member ensemble to produce hourly fields at 4.4 kilometers and 1.5 kilometers resolution. These include some full 3D fields. So the downscaling resolves fine scale structure of the tropical cyclones with more intense maximum wind speeds than we see in the Era 5 dataset. Chittagong and Cox's Bazar are particularly at risk of maximum tropical cyclone wind speeds exceeding 45 meters per second and 60 meters per second, respectively, in 5% of tropical cyclones that make landfall in Bangladesh. Finally, we look at a prototype warning model that is produced by combining the Bayesian predictive hazard distribution that we derive from our simulation of these 12 tropical cyclones with a loss function. So, starting with a look at the numerical modelling process. We run a Met Office regional model in a downscaling configuration using Era 5 data to initialize the model and provide boundary conditions. We run two modelling domains with model output available at 4.4 kilometers and 1.5 kilometers in a nested setup. This plot on the left shows the 4.4K domain in red and the 1.5 kilometer domain in blue. The boundaries for the 4.4 kilometer domain were chosen specifically to avoid interacting with the Himalayas, and the 1.5 kilometer domain due to the computational demand required to run simulations at this resolution was just restricted to Bangladesh itself. As a comparison for the different grid cell sizes, we can see in the right-hand corner here the larger square represents the size of the Era 5 input data. This is roughly 31 kilometers square. And by comparison, we have our 4.4 kilometer cell and our 1.5 kilometer cell. In terms of what the data resolution looks like in terms of the tropical cyclones that we're simulating, this is a visual comparison of the maximum wind gust for storm Sidr. And in particular, we're looking at the maximum wind gust over a 48-hour period, otherwise known as a footprint. So this is what Cyclone Sidr looks like in Era 5 data. You can see the individual block sizes, the grid size of the Era 5 data quite clearly. And when we use this to initialize our downscaling configuration, this is the output that we get from our 4.5 kilometer model and our 1.5 kilometer model. The scale on the right-hand side here is specifically the 10-meter maximum gust speed, going from around 15 meters per second up to 80 meters per second. And we can clearly see that the 4.4 kilometer model and 1.5 kilometer model really accentuates the high wind speeds that we see associated with the core of the cyclone. Looking then at our regional modelling configuration, we run a 9-member ensemble designed to limit the free-running model time to 72 hours. This limits the computation time required to run the simulations, whilst ensuring that the central 24 hours of interest, that is 12 hours before and 12 hours after the cyclone makes landfall, is sampled by each ensemble member. Together, our ensembles provide 9 simulations of the central 24 hours, but our simulations sample a wider period of 72 hours by running 3 hourly lagged forecasts. This allows us to use a range of initial conditions from which to start our downscaling, the benefits of which we'll see in a moment. Each run requires a 24-hour spin-up period as the regional model adjusts from the weak initial state inherited from the driving Era 5 data. This initial 24 hours is discarded in all subsequent analysis and data files, leaving us with 9 48-hour simulations. This is represented pictorially in this diagram here. So the orange star represents the point where the tropical cyclone I makes landfall. This grey box then is the central 24-hour period of interest, 12 hours before and 12 hours after the tropical cyclone makes landfall. And each of our 9 simulations going forward in time are represented by one of these lines. The 24-hour spin-up period is this dotted line here, and then the actual bits that we keep is represented by the solid lines, all moving forwards in time. So, in terms of what the ensemble members look like, on the left here is the maximum gust speed footprint from each ensemble member 1 to 9. Each footprint represents a physically plausible realization of how the storm might have evolved given the range of 9 different initial conditions. As the start time of each ensemble member gets closer to the true landfall time of the tropical cyclone, we can see that the ensemble members begin to converge towards what happened in reality, but they still retain some variation in the location and spatial extent of the hazard. The advantage is that this ensemble setup allows us to explore a greater range of tropical cyclone scenarios than if we were reliant on observations alone, or indeed a single numerical simulation of the event. So we run our ensemble downscaling approach for 12 historical cases listed here on the left, chosen in collaboration with Buet. These were constrained by the availability of the Era 5 data, which at the time of running these simulations only extended back to 1979. There are a range of meteorological variables available, including gust speed, which is the focus of this presentation, but also rainfall, air temperature, and mean sea level pressure, amongst others. These are all available at both 1.5 and 4.4 kilometre resolution, and all our data associated with this project is available under the Creative Commons Attribution 4.0 International License. Data compatible with the Oasis loss model framework is already available on the Oasis Hub data platform, and NetCDF model output is already available on Zenodo along with the data processing code. Finally, before we move on to look at some data validation, just a few words about the difference between the 4.4 and the 1.5 kilometre model data for 2 key variables. In this case, 1 hourly maximum gust speed and 1 hourly minimum mean sea level pressure. So for gust speeds, we see that the difference between the 4.4 kilometre and 1.5 kilometre data is relatively small, about half a metre per second faster in the 1.5 kilometre data. For mean sea level pressure, the 1.5 kilometre model has deeper lows on the order of 10 to 87 hectopascals, which suggests that the cyclones in the 1.5 kilometre model may also be smaller than in the 4.4 kilometre model. Now, all subsequent analysis presented here will focus on the 4.4 kilometre data, mainly for computational efficiency reasons. But further details of this 4.4 kilometre versus 1.5 kilometre comparison are available in a companion paper, the details of which I'll highlight later in the presentation. Moving on to discuss the validation of our data simulations. So this is an important step in any modelling workflow. However, there are no reliable sources of observational data for gusts, winds, or mean sea level pressures in this region with a sufficiently high sampling rate. Here we compare the 4.4 kilometre data to the source Era 5 data and the IB Tracks New Delhi and US forecast centres, including their estimates of uncertainty. So in these plots on the left, the Era 5 data is represented by the thick black line. The IB tracks data by the grey triangles, with the grey bars representing their associated uncertainty estimates. Our regional model data is shown as the coloured lines, noting that all 9 ensemble members here are plotted in sequentially darker colours. So we start with ensemble member number 1 over here on the left, ensemble member number 2, 3, and we end with ensemble member number 9 over here. Also note that the IB tracks data does not give an estimate of the maximum 3-second gust, so for the gust speed comparison we're only comparing our regional model against Era 5. So in general, the agreement between Era 5 and IB tracks is very variable for both wind speeds and mean sea level pressure, which we'll see in a moment. For very intense cyclones, such as this example of Cyclone Sidr in 2007, we can see that the difference is significant. Comparing the gust speeds of our regional model to Era 5, we can see that the peak gust speed is typically 20 to 60 meters per second, that is around 40 to 120 knots faster. But our regional model compares much more favourably to IB tracks, although we note that the timing of the peak in our model is often delayed compared to the peak in IB tracks. So here we're particularly looking at the wind speed comparison. So looking at mean sea level pressure, unsurprisingly we see a similar picture. Our regional model and IB tracks compare more favourably, with Era 5 apparently underestimating the depth of the pressure minima. Remember, Era 5 is this thick black line at the top, and these grey triangles at the bars represent the IB tracks with their associated uncertainty. Plotting the data in a different way, now only looking at the differences in peak gust speeds and the timing of the peak between our regional model and Era 5 across all 12 events, we again see that the timing of the peak gust speed in our regional model is typically delayed, i.e. later than in Era 5. So note in this plot that we are separating out each of the individual events. The thick green bar represents the ensemble mean, and the circles are each member of our ensemble. At the bottom, we summarise all 12 events into one box plot for the difference in timing here and the difference in the magnitude of the peak gust here. Finally, we can look at a comparison of storm tracks. In this case, we are only comparing our regional model storm tracks against IB tracks in terms of the density of tracks within a 30 by 30 kilometre spatial bin. These are the coloured cells on this plot. Darker colours show where there are more tracks out of a total of 9 passing through any given 30 by 30 kilometre bin. The IB tracks are shown by the blue and orange lines, with their estimates of uncertainty shown by the blue and orange dashed lines. And here we see that across all 12 events, 8 of the 12 have at least one regional model ensemble member with a track that makes landfall within the bounds of the IB tracks data. Notable exceptions to this are Viaru, BOB07 over here, and TC01B down here. Also noting that there's currently no track data available for Cyclone Fanny here. If you'd like any further details on any of the information that I've just shown here, there are lots more plots and analysis available in our paper currently under review in Scientific Data, the details here. Okay, on to the hazard analysis. So in this section, I'm specifically discussing what we can learn from our new simulations in terms of extreme gust speeds associated with tropical cyclones across Bangladesh. Starting with a brief overview of our statistical framework. Here we use generalized additive models, otherwise known as GAMs, to combine the information from each of our 9 ensemble members into one coherent, consistent spatial prediction. This is a very flexible statistical modelling approach based on generalised linear modelling that respects the spatial interaction present in our model data, but crucially it also uses the spatial dependence as a source of additional information when fitting the GAM. Now in practice, once we fit a GAM to each named cyclone, we can obtain an estimate of the underlying gust speed distribution at each grid cell of our model. From this distribution, we can fully quantify the uncertainty and variability in gust speed at every 4.4 kilometre grid cell over Bangladesh. Aggregating each distribution we get for each of our 12 named storms allows us to build a grand distribution of gust speed variability based on our numerical simulations. This image on the left shows how we progress from our 9-member ensemble up here via a Bayesian interpretation of a generalized additive model to estimate the parameters of the underlying gust speed distribution down here, which in this case is modelled as a log normal distribution. From the GAM at each grid cell, we derive the parameters of the log normal distribution, the parameters being the mean and the standard deviation, so that we can estimate this underlying log normal distribution at every grid cell in our GAM model. And from here, it is a trivial process to then pull out estimates of, say, the 95th percentile gust speed, which is what's plotted here. The limitation of this approach is that these statistics are conditional on events that have made landfall over Bangladesh. So this particular hazard analysis cannot be extrapolated to look at gust speeds in an area outside of the domain of the GAM. In this case, the domain of the GAM is exactly what is plotted here. In this case, the 95th and 99th percentiles of our gust speed distribution represent a 1 in 20 and a 1 in 100 landfalling event. These maps on the left now show the prediction gust speeds across Bangladesh for these 2 return periods, 1 in 20 here and 1 in 100 here. As you might expect, the coastal regions and southern provinces see the highest gust speeds associated with each of these return periods, but we can see that there is also an area in the north that could see gust speeds equivalent to those in towns and cities much closer to the coast. We can look at the same data in terms of event exceedance probability. So now these maps show the per event exceedance probability for the top 2 WMO tropical cyclone hazard levels used in Bangladesh. In other words, for a given landfalling tropical cyclone over Bangladesh, what is the likelihood that its gust speed exceeds either very severe cyclonic storm conditions on the left, equivalent to greater than or equal to 64 knots, and supercyclonic storm conditions on the right, equivalent to greater than or equal to 120 knots. Again, we can see that the coastal areas are most exposed to high gust speeds, with 1 in 5 to 1 in 2 landfalling tropical cyclones expected to exceed very severe cyclonic storm conditions. For the most extreme hazard level, the extent is much more limited, and these regions can expect the 120 knot level to be met or exceeded in 1 in 20 to 1 in 10 landfalling events, looking particularly at these regions around the southern coast. Looking at exceedance probability curves for 18 of the most populated towns and cities allows us to compare the exceedance probability for a range of gust speeds. Here we can say that, for example, Chittagong is roughly 2.5 times as likely to experience a landfalling tropical cyclone exceeding very severe cyclonic storm conditions, noted here, than, say, Dakar. So here Dakar is the thick orange line and Chittagong is the thick green line. noting that as we go up this scale, this is storm exceedance probability on the y-axis, as we go up this scale, the events become more likely. Finally, I want to briefly discuss how this hazard information can be incorporated into a decision-making framework. By defining the relative cost or loss of different actions, perhaps actions associated with different warning levels, we can use decision theory to identify the optimal warning based on our GAM-GUSPY distribution. In this case, using our GAM data, this warning model represents the most effective default warning that should be issued to minimize the loss based on historic tropical cyclone information. However, when specific forecast information becomes available, the same loss function can be used to issue warnings specific to that forecast. So in this case, our loss function is defined in this table here. And so we see that for a range of events, ranging from a relatively weak event to a relatively strong event, and a range of warning levels ranging from issuing no warning to issuing the most extreme warning, there is a range of loss associated with each of these. So for a very strong, a very extreme event, were we to issue no warning, we can see that the relative loss would be very high, say on a 100-point scale. Whereas for the same extreme event, if we issued a great danger, the maximum warning, we can see that the relative loss would be much lower compared to if we issued no warning at all. And so we can fill out this table defining the relative loss for each combination of these warnings and events. And we combine this with the information, the storm exceedance probability that we've derived from our numerical model, and we can use this to derive this optimal action. So this is only proof of concept. Defining the loss function is difficult and directly impacts the efficacy of the actions it recommends. In reality, one might define multiple loss functions depending on the type of exposure. So, for example, you could define one loss function for families who live in rural locations, and perhaps another for families who live in cities. Ultimately, the aim of this is really to translate data into a decision via a relatively transparent mathematical framework. Okay, so once again, let me highlight a couple of the publications which cover everything that I've just discussed in lots more detail. So I've already spoken about the paper that contains a lot of our validation analysis. But let me also highlight the paper that covers the hazard analysis. This in particular is already available online in the journal Natural Hazards and Earth System Sciences. Just search for this TOI. The data behind all of these plots is also available online via Zenodo, along with all of the code that produced the plots, which is mainly written in R and Python. It's available at this link here. And the hazard data compatible with the Oasis loss model framework is available on the Oasis hub at this link here. So that's everything I have to say. Thank you for listening. If you have any questions for me, please feel free to contact me via this email address.